Yes. So we have been talking about harmonic motion, um, for the previous lesson and so forth. And as you can imagine, a pendulum is a perfect example of an item, that or a device in a sense that undergoes simple harmonic motion, right? But in all of that being said, there are certain things that we need to know about a pendulum. Of course, one of those things is the period of oscillation, right? And so we're going to look at that in this particular um, lesson. All right. Now this formula here says that the period of a pendulum is equal to 2 pi times the square root of the length of the string that attached to the pendulum divided by gravity constant. Now today we want to derive it per se. All right. So we'll start out with this entire diagram here. Now what we're going to do, we're going to displace the pendulum to this amount called theta, of course. And we're going to just allow it to sit there in still air and just look at it and say, all right, what would be one of the main forces that is acting on this system? What do you think would be one of the main forces acting on the system, Isabel? Isabel, are you there?
Yes, sir. I'm now hearing you.
Oh, you weren't hearing me any at all?
No, sir.
Oh, okay. Sorry about that. Well,
I didn't know you started class already because I wasn't hearing you.
Oh, I'm not sure what happened. Yeah, because I'm not seeing Campbell, so I started. So we're looking at the overall pendulum, right? We want to derive the period of the pendulum, and in order for us to derive it, we have to obviously have a diagram that looks like this. That's where we have to start from. Okay?
Yes, sir.
Now, when the object is at this position, when it's at this displacement, one of the main force that is acting on it is the weight. And we know that weight is equal to mg. Now, as you can imagine, because this object, when it's at this displacement and you let it go, there will be a force that will bring it towards the center. Now, that force is going to be what we call the restoring force. And as the name suggests, restoring, it wants to restore the pendulum back to its equilibrium position, which is right at this point. But how do we find that that restoring force? What we would do is to resolve the force, resolve this weight right here into its horizontal and vertical components. So if I go ahead and resolve this force, the weight of the object, then I would realize that I'm going to get a component going like this and another component going like that, right? That's what we are getting when we resolve it. Now, one other thing about whenever we have anything that is in a circle per se, right? Let me just show you something here. This angle that is inside, that angle that is inside of the I would say, I don't know how to call it, but this angle that is right here, that's the angle that is going to be on the outside here. Some geometric kind of knowledge caused that to happen. I don't know how it happened, but we just have to just work with that to say that whatsoever this angle is inside, it's the same angle that will be reflected outside in between here when we do resolve these vectors into their components. So if the angle is in between this vector and this vector, then we can clearly see that this side is going to be mg cos theta. And if this side is cos theta, then the other vector, the other component of the vector is going to be mg, right? Um, sine theta. But it is not just simply mg sine theta. It's actually going to be negative mg sine theta. The reason for the negative is to just show us that we're going in the opposite direction, meaning that we're going this way. Whenever we're going towards the left, we signify that as being negative. So that's the reason why the restoring force, as you can see in the notes here, is going to be negative mg sine theta. But let me know if you follow what I did just now. So what we did is to resolve it into its horizontal and vertical component, right? And based on where the angle is positioned, we can know whether if this side is going to be cos or if this side is going to be sine. So because the angle is beside of that vector right here, then clearly it's going to be this side is going to be cos and the other side is going to be sine. So hence the reason why we're saying that the restoring force, we can call it Fr is going to equal to negative mg sine theta. If you have any questions, let me know.
So like in the exam, right?
Uh-huh.
Okay, would they would ask us like um actually never mind.
Okay, all right, no
Like I
problem.
think so like the angles from the top and the bottom are equal to each other, right? Like
Yes.
that's what we have to understand from the diagram.
Basically, yeah.
But are like there ever cases where they ask to find like a different angle besides like the angle that you've just shown?
If there's a case that they will ask us to find a different angle from that, is that the question you asked? You see, another way we could look at this, let me just see if it will make sense. Let me show you. So another way how we could look at it is from this standpoint of the whole aspect of Z angles, right? I'm not sure if they will ask you to find some other angle as relates to the question you asked, right? But another way how we could look at this to see whether or not this actually somewhat makes sense is by way of considering a Z angle, right? So what we'll do is to imaginary, draw a Z. So we're seeing this thing right here, this um, imaginary line basically. We're seeing the length of the pendulum. Then we're now going to draw another basically imaginary line right here. If we remember the whole knowledge about what we call it, Z angles in a sense, right? This angle right here is going to be the angle in between here. And if you know anything about circles, the angle opposite to this side is going to be the angle in between here. So that is also another way how we could look at it to find out whether this angle corresponds to this one. Because at the end of the day, this is going to basically form almost like a circle, so to speak. So this angle on this side will be equal to the angle on this side. So it's a whole lot, a little bit of maths going on right here, right? But at the end of the day, I'm not sure if you will get a proof like this. The whole reason why we're going through this is because, it's syllabus asks us to do it. You understand? Because you are doing the what we call it now, the lab exam. So chances are this could be something that the lab exam could ask. You understand? So we don't want to skip over some of these details. You understand? So one of the first thing we have to highlight here is that the restoring force, which is going towards the center, that's the force that is directed towards the center. We could almost refer to it as the centripetal force in a sense, because that is the force that is directed towards the center. Now, there are some things that we have to consider, where you see, in order for this to work perfectly, the angle in between here should not be greater than 100 degrees, right? It should not be greater than 100 degrees. And so for that reason, we 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 for that reason we say that sine theta is approximately equal to theta, right? So because the angle is very small, we come to an approximation to say that sine theta is equal to theta, all right? And we're going to see how that comes into play eventually when we move on to the next slide, right? So here is it now. If sine theta is equal to theta, then it means that we can substitute where sine theta is and leave theta. So remember we said now that force is equal to minus mg sine theta, right? But we said that because of the approximation, sine theta is approximately equal to theta. So we could go back and say, all right, minus mg theta, right? But theta obviously is not just the angle, it's the angular displacement, right? And if we recall anything about angular displacement is equal to the it's basically equal to the arc length, so to speak. So the arc length would be AC, which is right here, divided by L, So that is what theta corresponds to, right? So AC divided by L, that is what theta is equal to. And what we would do here is to take. Go ahead. Someone have a question?
Yeah, I was asking to repeat that, please.
Yes, so I was saying just now that theta, right, which is equal to the arc length, is equal to AC divided by L. AC divided by L. I don't know if you remember when we were looking at, what was this again, circular motion. Circular motion had something to say that theta is equal to S divided by R, right? So it's really the same thing, right? Where S is the that distance here, right? This arc right here, and obviously L in this case is going to be R, which is basically the radius. That's when we're looking at circular motion, right? But it's the same knowledge, so to speak, coming back into play here because harmonic motion is no different. There's no big difference between harmonic motion and simple and circular motion. They're almost using the same knowledge, right? So, providing that we know that the theta angular displacement is equal to this, right? Then we could substitute it in the equation now. So as you can see now, we're moving away from this standpoint, and we're now going to substitute what the angular displacement was, which is now AC divided by L. So at this point, our force is now approximately equal to minus mg times AC divided by L. All right. So that is what we have now. But there are other approximations that we're going to make, and which is the other one right here. So because we're dealing with small angles, which is in between here, what they're literally saying is that AC is just the distance from A to B. That's what they're saying, you know. That AC really corresponds to the distance from A to B. Because of the fact that you're using small angles, they're literally saying that if you were to really measure AC is approximately equal to AB, which AB is going to equal to X, right? Where AC is now basically equal to X, so to speak, all right? So having said that, we can now substitute, you know, for AC being equal to X. When we do that, we're now at this standpoint to say that the force, which we're taught, this force is restoring force, okay? Restoring force is approximately equal to minus mg, right? Times the X that I just showed you just now, which is right here, divided by the length of the pendulum. Now, the thing about this, guys, is that because the pendulum is swinging back and forth, we expect that there will be some amount of acceleration taking place. And if there's some amount of acceleration taking place, then it means that Newton's second law comes into play. From the mere fact that the thing is moving back and forth, some amount of force will be generated there, and Newton's second law would have stated that force is equal to mass times acceleration. So at the end of the day, our restoring force is equal to mass times acceleration, which is approximately equal to mg times x divided by L. Right? As you can see, the masses would cancel out, leaving us with A is equal to minus G times X divided by L. No, this is weird. Go ahead.
Excuse me, sir. Where did the X come from?
Yeah, the X came from this point. Let me just reiterate here. So because we're using small angles, it's almost like, you know, AC is equal to this thing here, which is just that distance, that distance from A to B right here. So this is where X is, you know, right? This is where X is. And we're saying because the angle is so small, then it means that if I were to measure AC, then it would basically be equal to X, which is just the distance from the amplitude to the center, right? Just that straight distance from the amplitude to the center. That's what they're saying X is equal to.
All right, sir.
Yeah. So having said all of this, we're at a point. You see, this is a critical point, you know, right? Because I don't know if Campbell had watched the previous video pertaining to this, because it comes back now, the whole aspect of simple harmonic motion. Because what you're going to see us doing is that we're going to compare the acceleration that we know for when something is undergoing simple harmonic motion. Anybody remember that equation that relates acceleration in terms of simple harmonic motion? Because it's an equation that we have to remember once we're dealing with simple harmonic motion for the acceleration. Do we have any idea as to what the equation is as it pertains to that? So we're at this standpoint where we have no yeah, go ahead.
No, sir, go ahead.
What were you going to say, Campbell?
I don't know if this is right. I think the formula would be wait, no, never mind. I was gonna say force equals to mass times the acceleration.
Oh no.
With the constant. No.
No, not that one. Yeah, you have to get back up to speed. All right. No. So one other thing right here we're seeing, you see, and I want you to see it, guys. Remember now that whenever something is undergoing simple harmonic motion, there are two main conditions that we can bank on for whenever something is undergoing simple harmonic motion. One of them is that the acceleration is directly proportional to the displacement. That x that we're seeing here, that x is the displacement, and I should have made mention of it a little bit better. So that x that we're looking at is the displacement, all right? So from this equation here, we're seeing that A is directly proportional to x. What that simply tells us is that the more I bring the pendulum further away from the equilibrium position, it's the more acceleration that it's going to have when it is going back to the equilibrium position. So we're seeing one thing already. We're seeing that A is directly proportional to X. All right. And obviously, once you have a directly proportional relationship, right, a constant comes into play, right? A constant comes into play. We can call a constant K for now. So we are saying that A is equal to K times X. Now, remember that for simple harmonic motion, the acceleration is always going in the opposite direction from the displacement. So if the object was displaced from equilibrium position to the right, then the acceleration will be going in the opposite direction. So that's what it means. Hence the reason why we have the minus sign. So the minus sign just shows us that the acceleration is going in the opposite direction of the displacement. So having said all of this, it shows us that a pendulum is undergoing simple harmonic motion just by looking at this simple equation here. And for that reason, for that specific reason, we can say that this acceleration is equal to the acceleration that we know, or we should know by now, that says A is equal to omega squared times X. This is the overall acceleration for when something is undergoing simple harmonic motion. Anything at all that is undergoing simple harmonic motion will have this acceleration. And as you can see right now, this equation is telling us that A is directly proportional to X, and also that the acceleration is in the opposite direction as the displacement. So the displacement is going towards the right, the acceleration is going towards the left, back towards the center. So from this, we're now going to compare both equations, right? And by comparing both equations, you're going to see what is going to happen next, right? So A, as we know, just know what we derived to say that A is equal to minus G divided by L times X. It is in the form of this. We can say that it is in the form as this, where A corresponds to this, right? The negative corresponds to the negative. The X corresponds to the X. So at the end of the day, we're seeing that this thing here, this G upon L, it must correspond to omega squared, right? Omega squared must correspond to omega squared because it is in the same format. So it's a format that we are interested in. Because it's in the same format, we are basically comparing the things in a sense. Or we could even do it two ways in a sense. We could do a thing like this, just to show you what's happening here, right? So one of the things we could do, we could equate this. We could equate it together. So if I take A equals to minus omega squared equal X, and then I write that A is also equal to minus G divided by L times X. What you're going to see happening here is that if I want omega squared to become the subject, right, then it means that this X needs to move from here. So I'm going to divide both sides by X. When I divide both sides by X, this X cancels out, this X cancels out, this X cancels out. So there's no more X on this in the equation. So I'm left with minus omega squared is equal to minus G, right, divided by L. This minus here, what purpose does it serve? Just blocking my way. So it's multiplying here. So I'm going to divide by minus 1. So if I divide by minus 1, I divide by minus 1 on that side. So what I'm left with is omega squared is equal to G upon L. And this is where I want to reach for now until I go to the next part. I did this to just show you what is transpiring. Why is it that we say that omega squared is equal to G divided by L? All right. So from time to time, guys, you will be tasked to compare things. You will be tasked to compare things. and this is one prime example, because the equations are in the same format, then we can simply say that omega squared is equal to G times G divided by L, because it is in the same place where G divided by L is in. So we could put the equations on top of each other. So A is equal to minus omega squared times X, just like that. So we're essentially saying that this corresponds to this. This corresponds to this, right? Minus corresponds to minus. A corresponds to A. So at the end of the day, what we're left with is omega squared is equal to G upon L. Comprende?
Yes, sir.
Now, having said all of that, what the aim of us doing all of this is to derive the formula for the pendulum, right? For a simple pendulum, whenever we want to find the period of a simple pendulum, we always use this equation, and I don't think this equation is new to us, but we are now deriving it, so to speak. So one of the things we have to recall here, I'm going to clear this off the screen. One of the things that we have to recall right here is that omega is equal to 2 pi divided by t, or we could say omega is equal to 2 pi f. I wouldn't use this one because I'm not trying to find the frequency. I'm trying to find the period. So I'm going to substitute that in this equation. So if I'm substituting that, this is what we're now seeing, that omega squared would basically be 2 pi divided by t, and in bracket this is going to be squared. So at the end of the day, we're saying that omega squared is equal to 4 pi squared divided by t squared. And for that reason, we're now equating this to G divided by L. Now, mind you, I want t squared. I want t as a subject, so I just need to do some transposition right now. So what we're going to do is this. I'm going to put it on this side. I'm going to transpose the equation. So if I'm transposing it, it means that t squared is going to go up there because I need it in the numerator, right? So that's the first thing I'm going to do. So when I do that, I'm left with 4 pi squared is equal to t squared times G divided by L. Having said that, I'm still not finished as yet. I want t at the end of the day. I still need to do some more transposition. So one of the things I'm going to do is to take the L and bring it across, right? So once I do that, I get now 4 pi squared times L is equal to t squared times G. I need to get rid of the G, so I have to divide both sides by G. So my G cancels out here. Now I'm left with t squared is equal to 4 pi squared, right, times L divided by G. Remember, we said that we want t, which is the period. So in order for me to get rid of the square, I have to square root both sides. Because in essence, the opposite of squaring a number is finding the square root. So I have to square root this side, and I have to square root everything on this side. When I do that, right, square root and square cancels out, leaving me with t is equal to the square root of 4 pi squared divided by L upon G. Now, as you can imagine, the square root of 4 rather, the square root of 4 is equal to 2, right? And if I said that the opposite of squaring a number is finding the square root, it means that the square root and pi squared is going to cancel out. So I'm now left with pi right? And then now I'm then left with the square root of L divided by G. So this is the overall equation, right? That we would have just proved just now pertaining to um, simple pendulum equation. All right. Any comments there?
Not really, sir. I don't know if I'll. This looks really long.
Okay.
So, yeah. So, is there any like? Never mind.
Oh, you're trying to
So
find a
I
shorter
have
way.
one question.
Yeah,
Sorry.
go ahead, Isabel.
Like in unit 1 and unit 2, like how many things are there that we could have like the possibility of having to prove like this, like deriving it?
Well, as it pertains to keep is well, there are so many things that we need to prove, and the most proof comes out of this area, right? In unit two, I know that there are a lot of things that they can ask us to prove as well, right? So we don't want to run the risk of not trying to remember these proofs, right? We should, because it explains how best we understand the concept as well. You understand? So we can't really run away from it. But I can't tell you definitively that say yo we might get this one or nothing like that, because as you know keep and all of that is uncertainty and all of that. So you know we just have to just accept it as it is. And
So
go ahead.
in the back of our head, we should have like a kind of way of like making proofs and stuff, like knowing the maths behind it and things like, how
Yeah,
they sometimes use simultaneous equations.
precisely. Yeah, yeah. We have to we have to have that back in the back of our mind. The way how we came from the question all the way up to this point, they require for us to know these things, from time to time. So
So could you find us like some specific questions like on doing proofs, and like we could send them back to you so we could practice?
all right. As I said, you see how the syllabus works as well, guys. There are times when you might not see one question pertaining to a proof, but the syllabus asks us to run through it. So may I say, chances are, what if that's the year when they decide to, want us to actually prove something of this nature, right? So yeah, that's pretty much. But I'll see what I can do. You see, and the thing is, sometimes we might not get a proof, but to understand the equation a little bit more, then it's good when we can see what is happening here. But I know it's a whole lot.
I'll oh
Go ahead.
I'll attempt this question.
Yeah, man. It's a more simple question than the proof, but we should not neglect it, as I said. Because what if you don't remember the equation, like the t equation that says t is equal to 2 pi divided by the length, you know, divided by g, something of that nature. What if we don't remember it, but we know how to prove it and get the answer? Then that helps in you knowing the equation or knowing the formula for it. But I know explicitly, or know for a fact, that for the next one that we're going to look at, they do ask us to. I've seen questions like that pertaining to prove or to derive it. So you'll see when we talk about it. But go ahead and see if we can solve this. I'll be back. All right. So we want to find the length of the rope. So what we're going to do is to use the equation. We're now trying to transpose to make L become the subject. So we're at this point now. We need to get rid of the square root sign. So we have to square both sides to get rid of the square root sign. And as you know, the opposite of squaring a number is finding the square root. At the end of the day, this square and the square root cancels out, leaving us with L divided by G, which is 9.8. 9.8. And of course, now because we're squaring this side, it becomes 4. It becomes 4 again. And of course, this becomes pi squared is equal to L divided by 9.8. We need to take that 9.8 and bring it across so that we get L as a subject. So L is now equal to 4. Well, basically 9.8 divided by pi squared. So let's see. Where's my calculator? So 9.8 divided by pi squared. I get something of this nature. It says 0.99.
Can you please repeat that, sir?
The answer I'm getting is 0.99.
For my answer, I got 9.7.
You got 9.7. Okay.
When I divided that.
We divide by pi squared.
Yes, sir.
Wow. That's dope. That's crazy because I mean when I had squared pi, I got 9.8 something something. So if you're to actually divide 9.8 divided by 9.8 something, then you're supposed to get something around here because around this.
Oh, sir, I realized my mistake. Instead of putting 9.8, I did 998.
Oh, okay. Well, make the mistake now,
Wait.
Yeah, I'm warm,
Nothing, sir.
You don't get the answer yet. Did you get the answer, Cam?
What was that? What was that, sir?
Did you get the answer?
Well, I wasn't finished yet. I was at the length over the constant gravity. I
Okay.
wasn't finished yet, sir.
Okay, cool. All right, I think that's just the only question there. But there's something spectacular that I want you to pay attention to. And it's related to the type of graphs that you can get whenever you are dealing with the period of a pendulum. All right. The first graph is t squared. This one that you're looking at here is t squared versus length. As you can clearly see, this is going to give you a straight line graph. If you're plotting t squared versus L, you're getting a straight line graph. If you're plotting t versus L, you're not going to get a straight line graph. You're going to get a curve, right? This and this is the same thing. This and this one is the same thing, all right? So it's the same graph. But let's just show you how you go about getting this line, this graph right here, right? So if we take the equation, t is equal to 2 pi times square root of L divided by G. Because we're plotting t squared, and before we would talk about that, you see, the two variables are that's in this equation that we're actually measuring is T and L. G is a constant, 2 pi is an arbitrary number. So for this experiment, you can clearly identify the variables. So it's T and L. So you know that already. What we're now going to do, this is what we call linearizing the equation. We're going to linearize the equation so that we essentially get a straight line graph. So the word linear means straight line, right? So at the end of the day, that's what we're trying to do. We're linearizing the equation. As is, the equation is not linear. The reason why it's not linear is because the square root over L right here makes it not linear, right? But we can make this linear if we want it. No, we can, but we don't want to do it as such. We're going to make an adjustment to it. So one of the first things we're going to do is that we're going to square both sides. So we're going to square both sides. The whole reason for squaring both sides is to get rid of the square root mainly. So when I do that, I now have t squared is equal to, remember now we're squaring everything. So 2 squared is 4, right? And obviously this pi is going to be pi squared. Now the square root is now gone because square root and square cancels out. So we're now left with L divided by G. This is our linear equation. It might not look linear to you. When we talk about linear equation, we are talking about the equation of a straight line. Equation of a straight line. And that equation says y is equal to mx plus c. Now this is where comparing stuff comes into play again. You remember we talked about comparing something a while ago around that side. In physics, we do a lot of comparing as well. So because I know the two variables that I'm plotting on my graph, I'm plotting t squared and I'm plotting L. Chances are this variable t squared is going to be my y variable. T squared is going to be my y variable. I know that L is another variable. So L is going to be my x variable. Now, let's look at this equation. The linear equation that says y is equal to mx plus c. Now, with this equation, wherever x is, there's going to be a gradient beside of it. M speaks to the gradient. M in this equation speaks to the gradient. So because my L, which is my x variable, is beside 4 pi squared divided by g, it now means that M, which is my gradient, is equal to all of this information right here. Following?
Yeah, I think so, sir.
All right. So having said that, the whole reason why we do this sometimes is to find an unknown, because there are times when they will ask you to find an unknown, and this unknown is going to be G. From time to time, they will want you to use this experiment to prove that G is equal to 9.8 and all of that. So what you would essentially do is you would plot a t squared versus L graph. When you find the gradient, which is your M value, that M value is essentially equal to whatsoever is here. But let me just show you now the finishing touch, right? Let me just see if I can. Well, all right, either way. So we have t squared, right, is equal to 4 pi squared divided by g times L. So at this point, I can do my final comparing. So this is the y variable. This is my m. This is my x. So y is equal to t squared. X is equal to L. M, which is my gradient, is equal to 4 pi squared divided by g. So chances are, somebody have a question?
No, sir.
Okay, good. So chances are, you would go ahead, you would plot a graph. Right? When you plot that graph, you're going to find the gradient. How do we find the gradient of a graph? Do we know how to find the gradient of a graph, or a straight line graph? Do we know?
Sir, can you please?
Like y2 minus y1 over x2 minus x1.
Exactly. Campbell, you were saying something a while ago?
Can you please repeat that?
I was just asking, how do you find the gradient of a line, of a straight line?
Oh, okay. Did Isabel answer?
Yeah, it's the answer, but I
Yeah,
wanted
y2 minus y1 over x2 minus x1. That's
yes.
Yes, sir.
So y2 minus y1 divided by x2 minus x1. So all you're doing, you're picking a point on the line. Mind you, the points that you pick, they must come from the straight line that you draw. It is recommended that you don't use the points that you plot on the graph to find the gradient, right? Just go ahead and pick 2 points on the graph, points that are appropriate, and then you find that would be your first point. So this point here is going to be your x1, your y1, then the second point here is going to be your x2, y2, right? So you do that, and we could do it. We could just try it, because I don't want you guys to let's actually try it. Give me a second here, because there are values on the graph, but we could actually just do it for fun, right? To just prove that G is 9.8 thereabout, right? So this is what we're essentially doing here. Okay. So if I pick a point here, for argument's sake, I'm going to try to pick a point that I can read. Right, so this is not completely accurate, so to speak, but so that is what you're actually doing. We're going to just do an estimate. So that's your gradient point. All right. Then now, let's see what other point we could use. Obviously, you would use your ruler to do this so that it makes it a little bit more easier for you. Right. So wherever it touches the line right here, that's the point you're going to use. I'm just saying that this is the T, which is my y2. My y2 value is going to be calling it at 4. Then now my y1 is going to be, let's just say 2.7. I'm just estimating that 2.7, right? And then your x2 now, my x1 rather, is going to be about 0.62. Then my x2 is going to be probably 0.995 for argument's sake. We're just going to just work with that for argument's sake. What we're doing here is to find the we're going to just find the gradient. Can somebody go ahead and try to find the gradient and see what we're getting in the meantime? So 4 minus 7.3 divided by 0.95 minus 0.62.
Wait, so that's a 0?
Yeah, it's a 0. Sorry about that. If it's right, it's not written properly. When I work out the first part, I'm going to do a little bit of erasing on this side. Right, when I did the numerator, well, the denominator, my bad. The denominator part is saying 0.33. It might not be accurate, completely accurate, but at the end of the day, we're just trying it out for argument's sake. 1.3 at the top. So I have 1.3 divided by 0.33. I get that the gradient. So my value of gradient is equal to 3.9.
3.9.
Exactly. So at the end of the day, this is your m value. And remember we said that m is equal to 4 pi squared divided by g. The idea is to find what g is equal to. So because m is equal to 3.9 equal to pi squared divided by g, we want g to make this become the subject, so we bring g across here, and we're going to take this and bring it across as well. So at the end of the day, we're saying that g is equal to 4 pi squared divided by 3.9. So when we multiply pi squared times 4, we're getting 39.4 divided by 9, not 9, but divided by 3.9. 3.9. I don't know if you guys did it, but I got something as to say 10.1 meters per second. The whole reason why we get this is obviously because the values weren't so accurate. Alright? But at the end of the day, those are some of the things that they might ask you to do. Alright? Isabel, are you still hearing me, or are you having challenges?
Yes, sir.
You're hearing me good, alright?
Yeah, well, most of the time.
Okay. So that is just what you would have been required here to do. Alright? Any questions related to this? What's her name again? Isabel, did we go through anything like this the last time that we met?
No, sir, we didn't go through energy.
All right.
No, yes, we did, sir. We did. Like we went through like the maximum kinetic energies, like in the middle, and like how you need to have like how the energy transfers like in the pendulum.
Mm-hmm.
And like the max energy and like the maximum like different types of energy, like kinetic energy. Yeah.
Mm-hmm.
Like that, yeah.
Yeah. So this is another thing that we must talk about first here when it comes down to the simple pendulum. right? Because what we're essentially seeing here is that energy is being transferred from one form or is being converted from one form to another form, basically, right? The two main energies that are in the system is potential and kinetic energy. Now, as you can imagine, potential energy is energy that is what we call stored energy, right? And potential energy is also related to height. So as you can see at this position here, when the pendulum is at this point, that is when it will be at its maximum potential energy. But not only that, that is when it's going to be at its minimum kinetic energy. Because what you realize is that if the object is not moving, then there's no kinetic energy. So we say that kinetic energy is equal to zero. But where's the kinetic energy going to? It has been converted into potential energy, right? But one of the beautiful things though, once we start the pendulum to move again, it's going to come to this point, which is the equilibrium position. Whenever it passes through the equilibrium position, what we're essentially seeing is that all of the potential energy that is coming from the system is going to be converted into kinetic energy, right? It's almost like something swinging close to the floor, right? It's almost like something you're swinging a ball on a string, and it is passing close to the floor. So imagine that this is the floor right here, and you're swinging that ball or a swing song coming to the floor. At this position, it's closer to the ground, so you would expect that it's going to have less height, which means that it's going to have more kinetic energy, right? Now, as you can imagine, the pendulum oscillates back and forth, so it's going to oscillate all the way up into the air like this, and comes to this point. When it comes to this point, it's going to have its maximum potential energy again, and then when it returns, it's now going to basically be converting the potential energy back into kinetic energy. But I must point out to you that at this point here, we say we have maximum K, KE, and it means that we're going to have minimum PE at that location, at the actual center, at equilibrium position. Right, Campbell? I know you probably weren't there at that time. So we
no, sir, I wasn't there.
Yeah, I know you weren't. We ought to maybe go ahead. Let us read up a little bit more about the energy system, what is taking place, right? But there are ways how we can. There are graphs that are related to the energy, and it's important that we understand these graphs, right? It's important that we understand these graphs because they can ask you to draw a graph that depicts the energy, right, of a simple pendulum, so to speak. So one of the first things, this is the equilibrium position. Obviously, equilibrium position means that you have zero displacement. When you displace your object to a certain point, then you're at the amplitude. So this is your positive amplitude. And then obviously, of course, let me just use a different color here. Right, so this is your negative amplitude. So that's essentially what is taking place. So you're oscillating, meaning that you're moving up and down, and all of that. Now, as it pertains to the energy profile in terms of the displacement, this is what we're seeing. That at maximum displacement, that is when you're going to have maximum potential energy. So if you look at the graph right here, my maximum is at this point. This is my maximum amplitude or maximum displacement. And as you can see, the red graph here, or the red line, shows that my potential energy is at the top right here, is at its maximum. As you let go of the object, so imagine that it's the thing oscillating back and forth. Imagine that this is the thing oscillating back and forth, right? Going up in the air, coming back to the equilibrium position, all of that. So as the object is going back to the equilibrium position, remember we're now saying that it is losing energy. It's losing energy. It's losing potential energy. When it reaches the equilibrium position, right, all of that potential energy is gone. It's no longer, it doesn't have any potential energy at that point. And then obviously going back up to the next amplitude, because that's how it works, it swings from one amplitude to the next. You would expect that it's going to go back to a point where it's now at maximum PE, right? So that is for the potential energy. As it relates to the kinetic energy now, as it relates to the kinetic energy, we can look at it as well to see what is happening as it relates to the kinetic energy. Now remember that at the maximum displacement, which is the amplitude, we said that that is when the kinetic energy is going to be equal to 0. So as you can see, this line is a 0 line, right? So there's no, essentially there's no kinetic energy at the amplitude. But as soon as you move the object from the amplitude back to the equilibrium position, what we're now seeing is that as you move towards the equilibrium position, right, that is when maximum kinetic energy comes into play. So as you can see, the graphs are opposite to each other, meaning that potential energy is at the lowest, kinetic energy is at the highest when you're at the equilibrium position. When we're at maximum amplitude, potential energy is at its maximum and kinetic energy is at its lowest. Sorry about that. All right, so we're just looking at the energy profile a while ago. So I think the last thing I was saying was that when we're at maximum displacement, you would have maximum potential energy. But as you can see on the graph, that is when my kinetic energy is at its lowest. So we ought to be able to describe this graph, and it just speaks to the variation, right, with displacement. All right, this is the variation with displacement graph, and displacement is just from the equilibrium position to the amplitude. Okay, guys?
Yes, sir.
All right, wonderful. All right. So there's also another graph that we could look at essentially, right? And this graph now takes into account the period of oscillation, right? I mean, we definitely have to look at it, I mean, to just see what is happening here. Now, mind you, remember that one period is when you oscillate the object from one point. So let's imagine that this is where I'm oscillating the object from, right? For me to count one period, I would have to record the time that the object takes to go to this amplitude and record the time that it takes to come back to the same amplitude. That would be one oscillation. And also the time taken to complete one oscillation is what we call the period. So let's now look at what essentially is happening with the kinetic energy as it moves, right, from the amplitude, right, from the amplitude all the way back to the amplitude again. So this is what is happening. So we're starting, I have less than a minute, so I'll restart the session and then now we pick up from there, all right?
Yes, sir.
This one is a little bit more harder to understand. It's a little bit more harder to understand, but we're going to look at it. Right, so we're starting at the amplitude. So just bear that in mind, that we're starting at the amplitude. And so this is what my kinetic energy looks like. So this is my kinetic energy going all the way up. This is when the object is passing through the equilibrium point. Let me just use this as the example because I think this would sort of like explain it a little bit better. So here we have the object coming from the amplitude, right? So that kinetic energy is now at the central point, which is the equilibrium, where we say that kinetic energy is at its maximum. We haven't finished the entire thing as yet, so let's go back. So going all the way up now to where it's now located, as you can imagine, it's going to come on this side, right? This is when my kinetic energy, right, is now at 0 again. That is when my kinetic energy is now at 0. Because as you can imagine, that kinetic energy coming from equilibrium position is going to be lost as it is going up. So right here is when you would have completed half the period, right? Half the period. And now, as you can imagine, the pendulum is going to come back. To the equilibrium position. So when it is now coming back, we're seeing here that this is what we're essentially talking about when it is now back at the equilibrium position. And then obviously it's going to pass that equilibrium position and go back to the amplitude, which is now taking the graph back to this point where we say that we no longer have any kinetic energy. So that is what is happening there. Okay, guys? And the same thing will occur when we have the potential energy, right? I don't think I need to go much into that, but at the end of the day, that was what we were looking at here. Right? So let's see what's next on this thing. So we ought to be able to can dissect this information. You will get it to read and to just put things into your own perspective, right? I would have explained it already. So that's just the notes right there. Now the next thing that we want to move on to, right, is talking about springs. Because what you would come to realize is that springs also undergo what we call oscillations, right? And not only that, they also observe simple harmonic motion. And this is another proof as well. I don't even know if it makes sense for us to even start it, but we can essentially start it, right, and see where it takes us. But in this regard, what we have here is a spring, you see, that is attached to a mass. So we call it a mass spring oscillator. Now it is oscillating, it's going to oscillate along a horizontal, right? So just bear that in mind, that it's oscillating along a horizontal. Now, I don't know how much we know about springs, but whenever you pull on a spring, the tendency of the spring is for it to return to its equilibrium position. And for it to return to its equilibrium position, the spring is going to have what we call a restoring force. That restoring force is equal to minus kx. Now, this principle of what we call Hooke's law, it's a very important principle for us to understand. And it says that, it states that, that the force needed to extend or compress a spring by some distance is proportional to that distance. All right. So the further away you pull the spring, right? It means that it's going to require a much larger restoring force to bring it back to the equilibrium position. Okay? So be mindful of that. That with an increase in extension, it's going to essentially.
Never seen each other videos.
Cambly, all right?
Yes, sorry.
I think. Huh? All right. Cool. So what we're looking at here is the fact that there's a force, as we made mention just now, what we call a restoring force, that is trying to bring back the object towards the equilibrium position. And because it's bringing it, yeah.
So I didn't hear it.
Up a lot. Like we're not hearing a thing you're saying.
Okay. Yeah, all right.
You had to stop talking for a while. I didn't hear anything.
Oh, the thing is, I'm recording the lesson. So if in any event that it didn't you know you didn't get everything, then you I'll send you the lesson eventually, right? But what I was trying to get at is the fact that once you pull the spring, right, it's going to restore back to its equilibrium position. Now the restoring force is moving in the opposite direction as when compared to the displacement or the extension. Because what we're doing, we're extending the spring towards the right, and there is a opposite force, which is what we call the restoring force, is bringing it back to its original position. So from here, we're seeing that the force is opposite to the displacement. That is the reason why we have the minus sign here that says force, and this is not Hooke's law that says force is equal to K times X, right? So we must remember Hooke's law in terms of how we go about stating it, right? Hooke's law really is just saying that, the force needed to compress or to extend a spring, right, by some distance X is proportional, not just proportional, but directly proportional to the distance, all right? I'm seeing that it's coming up on my screen to say that my internet is unstable, right? It's a long time it hasn't happened like this, right? When Campbell's internet is working fine, mine is not working fine. Campbell, you have to go and do something about your internet, right? Because it's affecting my internet. I guess that's what is happening. Because your internet is working good now, and now mine not working good because of your internet. Are you guys still there?
Yes, sir, but I'm hearing half of what you're saying. I think you're complaining that your internet is not working good because of somebody.
Yeah, Campbell's one causing it. Yeah, man. You realize, not blaming Campbell really, but what can I say? When Campbell internet now working,
it sounds like that, sir.
when Campbell internet now working, mine is working perfectly fine. But no, Campbell internet fixed now, so it means to say mine is supposed to.
Yeah, that's suspicious.
Yeah, something like one.
It's weird. You said we're going to do another proof and it went out.
Yeah.
You want to do another?
Even the screen lag this time.
Oh wow. Yeah, it's a bad event tonight. I don't know what's going on. It's really a bad event.
Hey, sir. So are we still meeting tomorrow? Because we can continue.
Yeah, but we're not finished yet. We still have more time to see me. Because you're hearing me good now, right? So yeah, possibility that we can meet tomorrow.
Yes, sir, we're hearing you.
Yeah, so that's just how the internet thing is working.
Pardon?
So we just have to what do I call it now? Yeah, but either way, what I'm saying.
So continue to prove because you're sounding good now.
Yeah. All right, so what we're really doing here is that we're equating the forces, right? So we know that because the thing is accelerating, or from the mere fact it's moving, then force is equal to mass times acceleration, but force is also equal to minus k times x. So we're equating both things to say that F times A, not F times A, M times A is equal to minus k times x. And so we can make A becomes the subject, the acceleration becomes the subject. When we do that, we're now seeing that A, which is the acceleration, is equal to minus k, right, divided by m times x. Let me know if you guys are still there. The thing keeps jumping up on my screen till my internet is unstable. So
Yes, sir, I'm still here.
all right, good. So we're at this point. You see, this is a very important point, guys. This is a very important point. It's not very hard to reach to this point, but it's no, what are we going to do with this point? This information here is just telling us that a spring has the whole ability of undergoing simple harmonic motion, which is telling us that the acceleration is directly proportional to the displacement, and also that the acceleration is moving in an opposite direction than the displacement. So that is what we're seeing from this equation. So for that reason, we can then equate the equation for acceleration when we're dealing with simple harmonic motion, and that equation is to say that acceleration is equal to minus omega squared times x. So because the equations are in the same form, as you can see, if we look at them parallel, you can see that A is equal to A, right? Omega squared is equal to K divided by M, and X is equal to X. So if we were to equate them, you would have seen that omega squared is equal to K divided by M. Are we still there?
Yes, sir.
Wonderful. So having said this, now is when we're going to recall. Now is when we're going to recall that omega is equal to 2 pi divided by t. What we're essentially doing here, guys, is deriving the period of oscillation for a spring, for a mass spring system. So because we know that omega is equal to 2 pi divided by t, we can substitute that right here to say that 2 pi divided by t all squared is equal to k divided by m. Having said this, we want t to become the subject. So we want t to become the subject. If we want t to become the subject, then we just transpose. But before we can even transpose, we have to expand, because there's a square right here. So we're getting 4 pi squared divided by t squared is equal to k divided by m. And by just transposing, you're going to see that so we're going to take t squared and bring it across here. So when I do that, I'm going to kind of like cut it short. I'm going to have 4 pi squared divided by m, right, times k is equal to t squared, right? I did that because I don't have enough space, but I'm just transposing, guys, and I think you guys kind of know how to transpose. So that's what I did. I just transposed to make t squared become the subject. All right, we're still there?
Yeah.
All right, and I don't think you guys are lost from here because I mean, all we're doing is making t square become the subject. So it means that I would have to bring t square across here. So t square is now across here. Then it means that I need to get rid of the m. Oh, wow. Let me fix something here. Let me fix something. I didn't do it correctly. So it's a good thing I didn't do it correctly. So that m is going to come across here. So m is in the numerator while k is in the denominator. So that is what we're supposed to have here. So now we have t squared is equal to 4. Obviously, we want to get rid of the square because we're trying to find t, which is the period. So we have to square root both sides. So we now have t is equal to, clearly, this square root, 4, square root of 4 is 2, right? And square root and square cancels us, leaving with pi, leaving us with square root of m divided by k. So when you're going through the information, right, this is the equation that we use whenever we're trying to find the period of oscillation for a spring. Because a spring will oscillate, guys. A spring will oscillate, meaning that it will go up and down. That's what we call oscillation. And if we want to find the period of oscillation, then we use this information. We use the fact that, 2 pi, times the square root of the mass divided by the spring constant k. So that k that you're looking at here, and in your reading too, you're going to have to find that, you're going to see that as well. That k is what we call the spring constant. The spring constant, that is what k is equal to. Let me know if you have anything here to say about this.
No, sir.
Yeah, but you sound so low. What happened?
What was that, sir?
You sound so low. You sound low, like like you're afraid. You're afraid of the physics.
Sir, I don't know what to say.
Yeah, it's a whole lot.
What was that?
Is it a whole lot? Is it a whole lot for you to digest?
Yes, sir, it's a lot. I'm worried. I'm so worried. Like, how am I going to remember? Or like, I don't know. I'm scared.
Isabel, what you say? Wait, Isabel.
Well, my thing with it is like I understand we have to kind of know the formula like in the back of our head to get like to derive it, and like we need to know what everything stands for and stuff like that. But like I think I need to do like practice with like deriving other formulas, and so I will understand like to see if I understand it.
I get you.
You know, really.
Yeah, I get you. I get you.
So it'll be nice if you could send us like some questions, and like maybe next class we could see if we understand how to derive formulas properly. Because I think once you get that concept, it would. I mean, it looks kind of scary, yes, but like I think we just need to learn it like maths.
Yeah,
I don't know how else to put it.
Yeah, that's essentially what it is. Yeah. But I mean, the most important thing though is for us to know the formulas that are related to whenever we're trying to find the period of oscillation. All right, that's kind of like the main thing, right? That we need to know. All right. That's
So I'm not hearing a thing you're saying right now.
You're not hearing anything.
No.
The struggle is real. I don't know. I was just saying a while ago that the main thing is for you to really know the equation though, like for both systems, the pendulum, and obviously the spring. All right, those are the main equations that we need to know from at this point. So
Yes, I understand what you're trying to say.
yeah, man. So from the definition of simple harmonic motion, we can see that anything that obeys Hooke's law, will result in what we call simple harmonic motion, right? So that's another thing. So if you see that something is obeying Hooke's law, which says that the force that is required to compress or to extend a spring, right, is directly proportional to the displacement or to the distance, so to speak, right? Once we're seeing that coming out in terms of Hooke's law, right, then it means therefore that it's going to observe simple harmonic motion, right? And also it says here that simple harmonic motion can also be defined as the motion of an object that results from a force that Hooke's law acting on it, right? So that was pretty much the final conclusion there. But guys, I mean, it really doesn't stop there in a sense, because what we looked at a while ago was for a horizontal spring. I don't know if you had seen that, but this what we came up with here was for a horizontal spring, right? There's no another derivation or derivation for what we call a vertical spring to prove the same thing here, right? All right, it's a whole lot just the same way. We as I said, I don't want to neglect it, right? But at some other time, I'm going to go through this just for you to see what is taking place and how we came by that equation again when we're looking at a vertical spring, right? Because who knows what card can play in any exam, so we don't want, and even with the you call it now the lab exam. But before we go right here, let's see what this question is saying. That it said that a mass oscillating on a spring, right, has an amplitude of 0.1 meters and a period of 2 seconds. It says that deduce the equation for the displacement x if time starts at the instant when the mass has its maximum amplitude or maximum displacement. So we want to deduce an equation for this. Campbell might not be able to relate completely to this question, right? But maybe Isabel can, right? You remember, Isabel, when I was showing you all of those graphs and all of that?
Sorry, sir, repeat that one more time.
Do you remember when I was showing you the different types of graphs that we can have and all of that when we start at different positions?
Yes, sir.
Yes, it's related to this this question. So we have a mass that is oscillating on a spring, my bad, and it has an amplitude of that amount of 0.1 meters. It has a period of 2 seconds. It says deduce the equation for the displacement x if time starts at the instant when the mass has its maximum displacement. It's a spring, so let's just imagine. Let's just look back at it. Here we have a spring, you see? This is your spring. This is prior to. So this is before we displace it. All right? Now, when we displace the spring, the distance from where the spring was originally, so this is like the starting point. The distance from where the spring was originally to where it's now at, that would be your extension. So what we're doing is trying to measure the extension, not necessarily, but what I just want you to see is that the distance from where the spring was, so this was before you pull it, right? So there's no force that you're applying to it now in this one right here, in this diagram. But as soon as you apply some force to the spring, you realize that it's going to extend. Now, it's going to extend to a maximum displacement. That maximum displacement is what we call the amplitude, which is 0.1 meters. All right, I'm just showing you the diagram for argument, just so that you can see it. You see what I'm saying here? Yeah? Hello?
Yes, sir.
Just wanted to find out if you guys are following with me, if you're seeing what I just did just now, as it pertains to the amplitude.
No.
No. Maximum displacement, you see, is equal to the amplitude. Maximum displacement is equal to amplitude. So at first, the thing was sitting here, it didn't displace, but as soon as you pull it down, the amount that you pull the spring down to, right? It's going to be 0.1 meters. That 0.1 meters is basically your maximum amplitude. Not only your maximum amplitude, it's also your maximum displacement, right? Now, having said that, they want us to consider when the object is starting from the maximum displacement. If you remember Campbell, anything that we said, not Campbell, but Isabel, if you remember anything about when we said that the system starts at the maximum amplitude, what equation would we take into consideration if we were starting something at the amplitude? Do you remember?
Don't we use force times mass times acceleration?
No, that's not necessarily what I want, right? The equation that I really want is related to displacement. That says that once you're starting at the amplitude, right, the graph is going to be a cost graph, right? Remember when we were looking at this? So this is X displacement, and this is T. We're starting at the maximum. We're starting here, and we're going down like this. I don't know if you remember. We're coming up like this. So that is what is happening here. You're starting at your maximum displacement, which is 0.1 meters. So this is what the graph looks like. Do you remember this now?
Yes.
What form of equation would we use here? Would it be cost or sine? Would it be cost or sine?
Sir, I'm sorry, what was the question?
I'm asking if the equation that we're going to use, would it be cost or would it be sine? Would it be a sine graph or a cosine graph? Campbell, I know you laugh. You know why you laugh? Because you haven't gone to watch that video as yet, right? I mean, I did send anytime I post a video, I send it in the WhatsApp group, and not only that, you said you would have had your notification on to see when the thing come up, right? So that I guess that's the reason why you're kind of a little bit behind in a sense pertaining to that part, right?
Would it
But
be
if would it be what? I didn't hear you. You said something? I don't know if you're hearing me. I'm not sure what's going on. But it's going to be a cost equation, right? So because you're starting at the amplitude, whenever you start at the amplitude, we're going to use a cost or a cosine graph, cosine equation, I should say. Whenever you start at equilibrium position, that graph is a sine graph. That's a sine graph, right? So once you're starting at this position, this is a sine graph, and it's going to involve a sine equation. The equation that we need here is going to be as such. It's going to say x is equal to x naught times cosine of omega t. Now x naught is the amplitude, right? Omega, as you would know, is the angular frequency, right? So having said that, we want to come up with the equation so we can now put in the information that we know. I know that my amplitude is my maximum displacement, which is 0.1 to 0.1 meters cost, but now I need to put in the value for omega. I can find omega using this equation. Omega is equal to 2 pi divided by t. The question went ahead to say that the period was 2. So it means that I can transpose to find omega. Well, I don't need to transpose because I have that information here already. So omega is equal to 2 pi divided by t. So at the end of the day, omega is equal to 2 pi divided by 2, which essentially is going to be equal to omega equals to pi, or we could say 3.14. So in my bracket, I'm going to put 3.14, and this is rad per second. Close the bracket, then I put my t on the outside. So at the end of the day, this is what we're essentially supposed to have. Good? To say that x, which is your displacement, is equal to the amplitude cosine of omega times t. So this is the equation. Yeah?
Yes, sir.
Campbell, you alright?
Yes, I'm okay.
Don't lie to me, no, Campbell.
Okay, I need to stop worrying so much because like anything mathematical like scares me sometimes, but I just need to chill out in this practice a bit. I think I'll be fine. I hope. I have to do it.
Yeah, you have to.
So I'm good.
Please watch the video, please, and just get the information, because you see, the thing is, what we have to understand is that we can't. If we skip out a video, it kind of go throw us off, because when we are gonna talk, you're gonna hear me talk about some stuff where obviously might not resonate, So it's important that we pay attention to those videos. A long time that video they post, you know, that video they post long time. So you should have watched it already. So go and watch that video because we don't want to delay and slow the progress. But yeah, it's a whole lot that went on here, especially in me explaining what was taking place, right? But at the end of the day, when they say deduce an equation for the displacement x, if time starts at an instant when the mass has its maximum displacement, if it tells us that, then it means that the equation is going to be a cosine equation because we're starting at the maximum amplitude. Whenever we start at the maximum amplitude, it's a cosine graph that comes into play. If we start at the equilibrium position, it's a sine graph. So please go from there. Go and review all of that material that we talked about previously, and then I'm going to post this one so that you can go back through again and to just see what's happening there. All right. So that's about it for today, guys. All right.